So I thought I would record just a little bit extra lecture because there's a few things I want to get to that kind of inform what you're doing in the cylinder lab this week or next week that we didn't get to, and since I'm missing lecture on Monday, this might be useful to you. So we're talking about turbulence and our lack of good understanding of it or prediction of it can lead to some like serious financial consequences and some underperformance or poor performance of things because we have to deal with turbulence or we can't predict how it's going to be. Now, we've been talking about the boundary layer plenty, so here's another one of those old NACA videos that kind of shows us a visualization of the boundary layer. So wind tunnel frame of reference, here's fluid flowing over a flat plate, and you can see immediately as soon as it meets that flat plate with a streak of dye, the flow next to the surface starts to get held back, and that boundary layer forms. It's something that you can measure, it's something that you can see, and it's something that we have to deal with on pretty much everything that we either send into space or drive or fly. And we've kind of danced around knowing that it's there, knowing that it has an effect, but we're going to get increasingly into the kind of the structure of it, how to calculate things about it, how to understand how thick it's going to be, how much drag it's going to cost us, etc. So you had this diagram in your notes, and we were talking about how the Reynolds number is kind of the defining factor for when transition will occur. So at a low Reynolds number you have laminar flow, and at a higher Reynolds number you're going to have turbulent flow. And that's essentially what this diagram is showing. It is not to scale, okay, so it's important that you realize not to scale in terms of how the boundary layer evolves, right? So you have free flow coming along here, and you see this x equals 0, so the Reynolds REX, the Reynolds number with x, that just means that the length scale that we're talking about is actually the x distance along a plate. So if we start at 0 meters, then the Reynolds number, the local effective Reynolds number is effectively 0. Flow hasn't started flowing over the object yet. If we go 100 meters downstream, then the Reynolds number characteristic length scale would be 100 meters. And that would lead to an extremely high Reynolds number for even a pretty low velocity. So you can see that eventually flow will transition. If it flows over something for long enough or through a pipe for long enough, eventually it will transition, whether you have slow moving flow or very low density or what have you. But it always starts out laminar. Every single boundary layer that forms is going to start out laminar, which remember doesn't mean smooth, but generally is quite smooth. Most of the flow is going in the same direction, and any disturbances get damped out. So you get this boundary layer profile that has a shape that we'll draw again and again and again, we'll get very familiar with, but it has that lower velocity near the ground, higher velocity away from the ground, same as we noted in our in-class experiment. Eventually the Reynolds number is going to get large enough that you enter this transition zone, right? So transition is where those disturbances stop getting damped out by viscosity. They start to take a hold, but it's not fully turbulent yet. So you have disturbances, but they haven't upset the flow in a kind of irreversible, irreparable way where suddenly you have all this crazy mixing in all three dimensions. So now that transitional area can be very long or it can be very short. Transition can happen very suddenly, as in, you know, over the course of a few millimeters, or it can happen over quite a while in 3 dimensions. Transition is super hard to predict, and so if there's an area of turbulence or an area of fluid dynamics that we still don't know the whole pieces of the puzzle, it would be in boundary layer transition. Free boundary layer transition, because the Reynolds number went up pretty high. But eventually that boundary layer will become fully turbulent. And that's where you have all that mixing, that recirculation, everything like that. Remember, this is not to scale, okay? So the turbulent boundary layer will be significantly thicker than the laminar boundary layer. Here on this page it looks like it's only slightly thicker, but that turbulent boundary layer will continue to grow and be just like massively thicker. Whenever we talk about the height of the boundary layer, we usually define it as being 0.99, so 99% of the free stream value. I guess on this diagram it's V, so we'll call it V infinity, will be the edge of the boundary layer, and in any realistic flow, like 99% is as much as you could realistically hope to measure. The edge of the boundary layer is not necessarily going to be some fixed point in space, some magical point where we always get that value. It's going to wander around in real life, but it's just convention to say, well, the edge of the boundary layer is 99% free stream. You go beyond that, you're into the free stream. The transition can be a bit wobbly, but the fully turbulent structure is pretty interesting. So because the Reynolds number is still dominant inside the boundary layer, you can imagine this, the V term, the velocity term, or U, or whatever you're using, inside the boundary layer, because we have this profile that tells us that velocity is very low next to the wall, even inside a fully turbulent boundary layer, you're going to have what we call a laminar sublayer. So that means the characteristic of a turbulent boundary layer next to the wall is that it still has a little bit of laminar flow right next to the wall, because the local velocity is very, very low, and that means the local Reynolds number is low, and it's below the threshold that turbulent flow would appear. Then you have, we'll get into the structure of the boundary layer in future weeks, but you have a kind of blending region, which is the equivalent of the transitional zone as the boundary layer grows along a plate. Even within any slice through the boundary layer, you're going to have this blending region, which is a bit like that transition. It's got a high enough Reynolds number where there are some disturbances and fluctuations. And then outside of that, there's the fully turbulent boundary layer. And we talked as well about how having slower flow next to the wall means that the faster flow that's coming along up here kind of gets pulled down. So there's a kind of rotational aspect of that flow, because it's going slower close to the boundary layer and it's going faster away from the boundary layer, and that's going to cause that kind of forward rotation. So boundary layers have high vorticity. So that local rotation of the flow. But that's also how the turbulent boundary layer draws momentum in, right? So the more rotation and mixing that there is because of the turbulence, the more it's pulling in energy from the free stream, and that brings momentum down into the boundary layer, which is why let me get a different color pen up. That's why if I draw what the boundary layer profile is for a turbulent boundary layer, it has a thicker profile next to the surface. And that is representative of the extra momentum that's been drawn in and given it that thicker profile. Again, we'll look at how the exact structure of this and how to calculate it and define it better in the next couple of weeks. But because a turbulent boundary layer pulls in momentum and shoves more momentum closer to the surface, it's more likely to prevent separation, because we talked the other day about how separation is almost like when it kind of runs out of energy and can't keep going around the corner. But if it has more momentum, if it has more energy in it, then it should be able to keep going around, for instance, in your lab, the cylinder for longer. So the reason in the lab guide why we're asking you to what we call trip the flow and make sure that it's turbulent, what we're hoping to do by that is drawing more momentum into the boundary layer and keeping it more energized as it goes around a corner that it otherwise might separate off of. So here's the thing. I said you can't really get turbulence back once something becomes fully turbulent. It's kind of like these disturbances have taken over and the viscous effects aren't enough to damp it anymore. But you can in fact reverse transition to turbulence by a few means. The most obvious one would be get rid of the boundary layer and start again. So there's been various, so this is the X-21 obviously, there's been various aircraft have been made where the wing, so on this one there are just rows of suction points on the wing, so there's a giant fan in the wing that is actually pulling air off. So that means as much as the boundary layer forms, you're actually pulling the boundary layer off of the wing, so that the flow coming over the top of the wing never really sees a boundary layer form, in which case it either stays laminar or it basically has a really low drag because it's not actually forming kind of viscous drag profile on the wing. And it was pretty successful. So there have been many other follow-ups like this F-16 where they drastically modified the wing profile, but they put on it what we call LFC, so that's laminar flow control, where again they were trying to pull off the boundary layer. Now the key to this is being able to get away with doing that without using more energy than you're saving. So if a turbulent boundary layer causes more friction and more drag, then whatever you're doing to get rid of the turbulent boundary layer should hopefully not use a lot of energy. Otherwise you're going to end up using more than you're saving. So there's a lot of effort being going into how to avoid that and how to make sure that if you have suction holes and things on a wing that they're not clogging up with insects, etc. You can also see here, though, they said among the many things they're measuring, they had microphones. And that's because you can literally hear the difference between a laminar and a turbulent boundary layer. So in a laminar, if you put a stethoscope up to the underside of the wing or a body or even the side of our wind tunnel, we've done this before, then if it's laminar, you can hear a very kind of quiet, kind of whistling noise, and when it's turbulent, you hear a lot more like what you hear when you roll the window down on your car when you're going at speed, and you hear that kind of louder noise. Sometimes you hear frequencies like because of vortices and things that are forming that don't normally form in laminar flow. So having microphones embedded in the aircraft let them determine where the flow was laminar and where the flow was turbulent along the wing. And this technology has actually crept in a little bit. So the 787 tailplane, they didn't make a lot of this when it came out because it's kind of brand new technology. But what they actually have on the tailplane of the 787 is a boundary layer blowing system. So instead of pulling the boundary layer away, what they do is they have blowing, where if you can imagine the boundary layer profile looks something like this, right? So the height away from the surface versus the velocity. This gradient in here, the gradient of the plot there, so how quickly the velocity reduces to zero at the wall, determines how much friction, how much energy is being lost to friction. But if you introduce boundary layer blowing, then you're increasing momentum at the surface. So now you don't have such a large gradient. It doesn't go to zero anymore. The boundary layer profile might look something like that. And so you don't have the loss of energy that is involved in bringing the velocity all the way to zero at the wall. And that's really useful for something like the rudder on the 787, where if they can get better performance, lower drag, and also energize the boundary layer so that it doesn't separate at high rudder deflections, then you can have a smaller rudder on the aircraft, which saves weight, and it also increases the performance of the whole aircraft. So that's pretty clever technology that's been around for a long time, but it's never really been implemented properly because of materials, because of the weight of the suction and blowing devices that people have looked at. But things always get smaller and lighter. We're innovative, we're aerospace engineers, and now you're seeing this pop up on aircraft quite a lot. And it's my hope that it's only a matter of time before we start to see this on road vehicles and things as well. Anyway, so here's our guy Prandtl. Prandtl basically discovered the boundary layer. It's not like he invented the boundary layer. The boundary layer always existed, but he basically discovered it, and he did a lot of experiments in his little water channel that you can see right there. Kind of probably reminds you of some labs you've had at Cal Poly. But anyway, Prandtl's like the father of the boundary layer, right? So there was this guy that was after Bernoulli, but before Prandtl, called D'Alembert. I assume he was French or Belgian or something like that. You'll notice that he's gazing longingly at Prandtl's beard here, and it might give us some indication as to whether it's actually better to have a beard or not if you are going to make fluid dynamic discoveries. Because D'Alembert's paradox, here's his problem. He was working off of Bernoulli's equations, and he was working out, okay, if I have incompressible, inviscid flow around an object that's streamlined, then mathematically it shouldn't produce any drag. But in real life, we know that of course something would produce some drag. So he had a set of equations that said this shouldn't happen, but then he had real life observations that said it could. This seemed like a bit of a paradox, and nobody was able to put some math on why this was happening until Prandtl came along. Now, when Prandtl came along, he had one paper. I want you to think about this when you're writing in your lab reports, turning in your lab reports. He wrote a single technical paper that introduced a whole bunch of very useful concepts. Oh, by the way, his student was von Karman. We were talking about von Karman the other day with the vortex street. So he begat von Karman and many other famous names that we'll come across. Anyway, so he wrote one paper, and in this paper he outlined the concept of the boundary layer and a set of equations to describe it. So he was the first person to really, call it a boundary layer, and give it an actual mathematical definition, a set of equations to describe. And he was working off the Navier-Stokes equations, which already existed at that time, but were very highly unsolvable. So he had to make a bunch of simplifications to take a kind of nonlinear parabolic set of partial differential equations and turn them into an ordinary differential equation set to describe it. So he reduced the Navier-Stokes PDEs to ODEs and validated that. So he actually checked to make sure that that was a decent assumption that he made, or a decent set of work that he did to simplify and still get something that's physically realistic. He also, in this same single paper, came up with a formula for friction drag. So he didn't just say, hey, here's a boundary layer, here's what it means, here's what it does, here's how you would figure out where the boundary layer is or how thick it was. He said, well, here's what it means as well. This lets us calculate what the friction drag on a flat plate or something would be. He didn't stop there. He established that flow separation depended on the pressure gradient. So he did a set of experiments to show this, that if you play around with the pressure gradient of flow over something, then you can manipulate it to produce separation or not produce separation. And then he also proposed in the same paper that you can control the boundary layer with suction, which was what we were just talking about. So he basically invented boundary layer flow control. As soon as he discovered the boundary layer, he figured out all the important things about it and then how you can control it. That is a hell of a lab report. Well done to you, sir. My hat off to you, Prandtl. Well, your hat is already off, Mr. Prandtl. And so if we were going to try and visualize, so you can't visualize exactly what's happening at the surface because you can't really see exactly what's happening right next to the surface. Anytime you inject smoke in, it's going to have a buoyant effect away from the surface, and then as it becomes turbulent, it's going to mix and disperse. But the best you can do is kind of see the echoes of what happens, where, look, here it's coming in nice and laminar, and then you get into this transition zone where some of the flow is starting to become disturbed and turbulent, but it's not really taken over. And then by the time you get here, it has, those disturbances have taken over, and now you have a fully turbulent flow field. Another visualization that you can see for turbulent boundary layers is using infrared imaging. So we use this in our wind tunnel quite a lot. This is a high speed flow one, but we use it at low speed as well. Where because the turbulent boundary layer has increased mixing and increased energy, so that means it has an increased heat transfer rate. It's able to disperse kinetic energy and heat through the boundary layer because it is tumbling and spinning and mixing a lot more than a laminar boundary layer. So whenever you see a wing that's being heated or cooled, either by a heater or your model's been in the freezer, or it happens naturally in supersonic flow because the wind tunnel cools down quite a lot, you can use infrared imaging to start to see usually these things like the turbulent wedges. So that tells you there's a little bit of transitional behavior, or little bits have gone turbulent and other bits have not. and then by the time you are out of that zone, then the boundary layer has become fully turbulent over that wing. So you can literally visualize where transition is on a wing using visualization with oil, like we showed for a glider a couple of weeks ago, or infrared or something like this. But it all depends on the Reynolds number. So if you have Reynolds number of less than 1, that's kind of like the green dye flow over the cylinder that we saw the other day. You've got laminar flow, but even more than that, it's what we call creeping flow. There's absolutely no chance this can ever go turbulent. By the way, I should point out that this is only for external. It flows in a pipe. It tends to transition a lot earlier because the influence of the boundary layers is way more important because they're growing right off the surface and they tend to merge and join, and the surface can have quite a large effect. But if we have unbounded flow like an aircraft or a spacecraft, these kind of Reynolds numbers would apply. So Reynolds number less than 100, you still have laminar flow, but it's already changing a lot with Reynolds number. So if I increase the Reynolds number from 1 to 10, I'll see a big change in the behavior of the flow. If I increase it to 100, I'll see another change again. If you start getting up to 10 to the minus 3, then, hey, flow's still laminar, but it changes, I would say, a little. And this is the kind of zone that you're in for your cylinder lab, where 10 to the minus 3 is probably the low end of the spectrum that you can get with laminar flow, and you're going to see a specific vortex shedding pattern. After that, you're going to be into some kind of transitional. So that really what I mean there is that it could be laminar, or it could be turbulent, or it could be some combination of both, but it's going to be really hard to predict what it should be, so transitional-ish. But really by the kind of, certainly by 10 to the 5, 10 to the 6, you're almost certain. It'd be a miracle if you can preserve laminar flow past that. So turbulent, but it also changes with Reynolds number. So it can effectively become more turbulent, flow over a cylinder or flow over a wing. You would see different separation points, or you would see different drag and things like that. But if you kept increasing the Reynolds number, so let's say you kept increasing the velocity, then that would stop changing. So it's turbulent, but it doesn't really change its behavior much with Reynolds number. All right, so here would be flow through a duct, a converging diverging nozzle, and so this is a velocity profile here. So it's showing you what the velocity is looking like. You can see it's slower at the wall, faster in the middle. That's becoming quite familiar to us. And then we've got a boundary layer growing on the wall as it comes along the wall there. So you can see how as the flow constricts through the throat of the nozzle here, the middle of the flow is going to speed up a lot. It's obviously still 0 at the wall because of the friction that's happening at the wall. So now you have a really large gradient, and then as the flow starts to slow down again, you start to see some interesting effects that lead towards flow separation. Okay, so here you have a little what we would call point of inflection. Where you can see the kind of the shape of the boundary layer starting to change. It's not all just this convex shape. It has a little bit of concavity because it's been forced through that nozzle, and the middle flow is slowing down, and then there's a kind of change of behavior at the wall because the boundary layer is growing and expanding in that region, right? You can see how the boundary layer here and then the boundary layer here is getting a lot thicker because it's slowing down. So the faster the boundary layer, the faster the flow is, the thinner the boundary layer is going to be because momentum pushes it down close to the surface. And then as you start to slow down again, the boundary layer actually gets thicker. But as it slows down, you're taking momentum out of the flow. Okay, what was once a really fast flow is now slowing down. It's losing steam, running out of energy, to the point where eventually, the wall shear stress, so tau at the wall equals 0, so wall shear stress, the drag basically, becomes 0. The flow doesn't have enough momentum and energy to hang onto the wall anymore, and so it separates, and you get the backflow region, or the recirculation region, because of that. Now, you can see there's now an interesting thing where it's not really a boundary layer profile like we know or recognize it. Some of this flow is going backwards, and then some of this flow is going forward, so it's almost like the boundary layer now forms along this little slip line here, but there's no wall there or anything. That's just where the recirculation zone ends. So you can see that's where the shear layer would be. Delta, by the way, is the height of the boundary layer. So if we're talking about, okay, y is the distance away from the wall, but the height to our 99% of free stream velocity is delta. But if we were to draw what the pressure distribution is, so if we were to draw just really simple pressure along this line, then as we go into the nozzle, so it's speeding up, so that means our pressure is going to drop, and then as it slows down again, our pressure is coming back to where it was before, and then suddenly when it gets up to here, it's going to separate. And sometimes we talked about how separated flow sometimes has quite a lot of low pressure because it can be recirculating. So at the point of separation, there'll be a very sudden jump. But as this pressure is reducing, we call that a favorable gradient. Favorable as in this is getting faster, it's got more momentum, the boundary layer is more likely to stay attached, it has more energy, and then as we come up here with increasing pressure, we call that a adverse gradient. Adverse meaning that it's running out of momentum, it's losing energy, and therefore it's more likely to eventually separate. Which is why when we saw in that video the other day, separation on the wing as it pitched up happens towards the rear of the wing, not where it's having the most acceleration. But then if you keep pitching, it will happen at the leading edge because it just can't turn that corner anymore. And so the golf ball situation is a pretty interesting one, right? So the golf ball is all about if you had a smooth ball that had a lot of drag coming off of it, then your golf ball wouldn't go very far. It would also be quite unstable because you've got this wobbly, vortexy flow coming off of it. And what adding dimples to the golf ball does is it adds extra energy into the boundary layer. So by creating more turbulence and disturbances in the boundary layer, that is drawing momentum in, and it's allowing the flow to stay attached for longer around the golf ball. It's the equivalent, as you can see in this diagram, of having a smaller frontal area on the golf ball, because really the wake is the main driver for drag on that ball. If you reduce the size of the wake or the thickness of the wake, the velocity deficit, then you're effectively reducing the drag on the whole golf ball, and the ball will go further. And because the vortex shedding is a bit more under control, it will be significantly more stable as well. And so again, that's what we're kind of asking for you to do in your cylinder lab, or to analyze whether, if you tried it in the lab, putting some kind of vortex generation on, be it sandpaper, be it whatever you did you manage to affect the separation point by increasing the turbulence in the boundary layer, increasing the momentum in the boundary layer, to keep the flow attached for longer. But people get a bit confused about the golf ball because there's dimples everywhere. And the only reason you need dimples everywhere is because the ball's spinning around. So you don't know where on the surface exactly it's going to separate. In any normal situation, if you only put dimples right before the flow is going to separate to kind of energize the boundary layer, so you would only put, if this wasn't spinning, you could only put dimples or some kind of roughness there to energize the boundary layer, and you would affect the separation point right here. You wouldn't need to have dimples everywhere. Only on the ball because it's spinning in random ways. But people don't always think about that because people aren't trained aerodynamicists like you guys are. So they start to put it on crazy things like, oh, dimple enhanced fan technology for a desktop fan, which might help, but wouldn't you just want to design fan blades that don't separate in the first place? I don't know. Doesn't seem like a huge problem to me. And then this is Nike running suit on the right here, where they were trying to use dimples on the running suit to see if it would make a sprinter run faster. Now, a person does have flow separation off their arms and legs and body. And Nike did claim that there was a very slight advantage to doing this, but the ability of a runner to run in the exactly same way, in the exact same wind conditions, on the exact same track, time and time again, enough to get a fix on whether that was actually helping is pretty limited. You'd have to do some seriously controlled wind tunnel tests or simulations to get a benefit from that. But hey, it could work if you were putting those dimples right before where you think you're going to have flow separation. There it kind of looks like they just sprayed dimples around to make it look cool from the future. And then the most notorious example, last of all, is of course the Mythbusters dimple car. Now, if you watch this episode of Mythbusters, they will conclude that the dimples actually increase the efficiency of the car, so it reduced the drag of the whole vehicle. I know the people at NASA that did the wind tunnel tests on this, laughing as they did it, because hopefully by now you can already see that there's no way that will reduce the drag on the vehicle. It will dramatically increase the friction drag because the boundary layer will be all turbulent and much thicker and much more drag than if it was thin and smooth and laminar. If they put only the dimples off of the back of the car, so, or maybe, on the areas where it separates, so the A-pillar, the back of the car, off the rear end of the car, maybe around this frontal area, then you would help control separation that might already be happening on the vehicle. Putting it all over the vehicle is crazy stuff. But I think Mythbusters have the same problem that Nike has, where they could not get decent repeatability on their tests. They simply did it a couple of times, and one was better than the other. But there is no chance, there is no way that putting golf ball style dimples all over a vehicle is going to actually reduce the drag on your car. So please don't try it at home. Do not get out a hammer and start bashing holes in your car. It's a terrible idea, and you as a trained aerodynamicist will now know that this is a terrible idea. But go to town on the cylinder and see what you can get away with in terms of tripping transition and making that boundary layer turbulent, energizing the boundary layer and keeping it attached, keeping drag down, keeping the wake down. Alright, good luck.